Rainbow. A rainbow is produced by the reflection of sunlight by spherical drops of water in the air. Figure shows a ray that refracts into a drop at point A. So that refraction occurs at point A. Angle of incidence theta sub A at point A. Angle of refraction theta sub B at point A. Is reflected from the back surface of the drop at point B. So angle of incidence theta sub A at point B, angle of reflection at theta sub R at point B, and refracts back into air at point C, angle of incidence theta sub A at point C, angle of refraction theta sub B at point C. This is where refraction occurs. The angles of incidence and refraction, theta sub A and theta sub B, are shown at points A and C, and the angles of incidence and reflection, theta sub A and theta sub R, are shown at point B. Part A, show that theta sub A at point B, angle of incidence at point B, is equal to the angle of refraction at point A. Angle of incidence at point C is equal to the angle of refraction at point A, and angle of refraction at point C is equal to the angle of incidence at point A. So we have to show these three. Okay, so if I look at this geometry carefully, I see that drawing the connection between point A and the center point here, OA distance is equal to OB distance is equal to OC distance. So I have these three distances equal to the radius of the sphere. So I can note that since OA distance is equal to OB distance, this triangle AOB triangle is an isosceles triangle. If this triangle, AOB triangle, is an isosceles triangle, we can conclude that angle of refraction at point A is equal to angle of incidence at point B. So then we can conclude that angle of refraction at point A is equal to angle of incidence at point B. So that was the first thing we have to show. Angle of incidence at point B is equal to angle of refraction at point A. Now, if I look at the reflection at point B, law of reflection tells me that the angle of incidence and angle of reflection should be the same. So I note that at point B, angle of incidence at point B is equal to angle of reflection at point B. This is due to law of reflection. And looking at this triangle, BOC triangle, I have another isosceles triangle, which is telling me that the angle of reflection at point B and angle of incidence at point C must be the same. So, since the length of OB is equal to the length of OC, AOC triangle is an isosceles triangle. Therefore, I can conclude that the angle of reflection at point B must be equal to angle of incidence at point C. So combining these three equations, I can see that the angle of incidence at point B, theta sub A at point B, is equal to theta sub B at point A. That's the first equation here from this AOB isosceles triangle. But since theta sub A at point B is also equal to the angle of reflection, it's also equal to theta sub A at point C, angle of incidence at point C. So I have shown that the angle of refraction at point A is equal to the angle of incidence at point C. Angle of refraction at point A is equal to angle of incidence at point C. And finally, I have to show this. Angle of incidence at point A is equal to angle of refraction at point C. To do that, I'm going to write Snell's law at point A and Snell's law at point C. So if I write Snell's law at point A, we have index of refraction in air 1 times sine of the angle of incidence at point A, sine theta A at point A, is equal to index of refraction of the droplet and sine angle of refraction at point B, point A, theta sub B at point A. And at point C, I have angle of incidence, sine of the angle of incidence at point C. The ray is coming from the droplet, so it's n times sine theta sub AC is equal to 1 times sine theta sub B, angle of refraction at point C. All right. And since theta sub B at point A, theta sub B at point A is equal to theta sub A at point C, I can write also sines of these angles are the same. So sine theta B A is equal to sine theta A C. So looking at Snell's law here, 1 times sine theta A at point A is equal to n times sine theta B at point A, but sine theta B at point A is equal to sine theta A at point C. So this is also equal to n times sine theta A at point C, which is equal to, from the Snell's law at point C, sine theta 1 times sine theta B at point C. So comparing these two, I can see that the angle of incidence at point A, theta sub A at point A, must be equal to angle of refraction at point C. So this conclusion I have reached using Snell's law written at the 2 points A and C. So that answers the first part of the question. Part B, show that the angle in radians between the ray before it enters the drop at A and after it exits at point C, the total angular deflection of the ray is delta equal to twice the angle of incidence at point A minus 4 times the angle of refraction at point A plus pi. There is a hint, find the angular deflections that occur at these 3 points, A, B, and C, and add them up to get the total angular deflection. Okay. So, if this incoming ray was not deflected, it would go on a straight line like this. So you can see instead it bends towards the normal to the surface, and the deviation from its original path is delta sub A. So the angle of refraction at point A plus delta sub A is equal to the angle of incidence at point A. So that's our first observation. So we can write the angle of refraction at point A plus the deviation angle at point A is equal to the angle of incidence at point A. So the first deviation that occurs at point A is equal to the angle of incidence at point A minus the angle of refraction at point A. Now let's move on to point B. If this ray was not deflected, it goes on a straight line like this, it would follow this path. Instead, it goes through this path, and there is an angle of deflection theta b at point B. So you can see that if I add the angle of incidence at point B, theta sub A point B, the angle of reflection at point B, and the deviation delta B, it adds up to pi. So this whole thing adds up to pi. So I can write theta sub A at point B plus theta sub R at point B plus the deviation at point B adds up to pi. So for the deviation at point B, I can say it is pi minus the angle of incidence at point B and the angle of reflection at point B. Now you know that these two angles are the same because of law of reflection. I can write this as pi minus twice the theta A angle of incidence at point B. Now moving on to point C here, if this ray was not deflected, it would follow this path, but instead it was deflected by an angle delta C here. So you can see that this angle theta sub A at point C plus the deflection adds up to the angle of refraction at point C. So let's write that equation here. The angle of incidence at point C plus the deflection at point C is equal to angle of refraction at point C. So this angle, which is this angle here, plus the deviation adds up to this angle, angle of refraction at point C. So I can write the deviation at point C is the angle of refraction at point C minus the angle of incidence at point C. Now what is the total deviation? Delta. It's the deviation at point A plus deviation at point B plus the deviation at point C. For point A, I have theta sub A at A minus theta sub B at A. So the first term, theta sub A at A minus theta sub B at A. The second term, the deviation, is pi minus 2 theta AB. So plus pi minus 2 theta AB. And for the third term here, I have this theta sub B at C minus theta sub A at C. Okay. Now, theta sub A at A, angle of incidence at A, is equal to the angle of refraction at point C. We have shown that in part A. So these two are equal. Now, the angle of refraction at point A is equal to the angle of incidence at point B because of the isosceles triangle, which is also equal to the angle of incidence at point C because of another isosceles triangle. So these three terms are equal. So I can write the total deviation delta is equal to 2 times theta sub A at point A, angle of incidence at point A, minus 4 times the angle of refraction at point A, because 1, 2, 3, 4 of the same thing. And then I have this angle pi plus pi. So this gives me the total deviation delta. So let's move on to part C. Use Snell's law to write delta in terms of the angle of incidence at point A and index of refraction and of the water in the drop. All right. Now Snell's law at point A. 1 times sine theta A, angle of incidence at point A, is equal to n times index of refraction of water sine theta B, angle of refraction at point A. So instead of sine theta B at point A, we can write sine theta A sine theta A at point A divided by n. So this is Snell's law written at point A. Okay, so I can see that the angle of refraction at point A, theta sub BA, is nothing but arc sine theta sub A at point A divided by n. Then my deviation can be written as twice the angle of incidence at point A minus 4 times arc sine or sine inverse sine theta A at point A, angle of incidence at point A, divided by the index of refraction plus pi. So our task was to write the deviation in terms of the angle of incidence at point A and index of refraction, and that's what we have done in this part. Okay, so first of all, we wanted to determine the relationship between these angles. So following the refraction here we have theta A going to theta B angle of refraction at point A. And because from the center OA distance, OB distance, and OC distances are the same, these are isosceles triangles, and there's reflection here. Law of reflection tells us that these two angles are the same. We conclude that these four angles are equal, and because Snell's law applies here, 1 times sine of this angle is equal to n times sine of this angle. Then n times sine of this angle is 1 times sine of the same angle. So these two angles must be the same. Then we wanted to determine the total deviation of the beam from its original path. To do that, we looked at deviations at 3 points. At point A, the deviation delta A plus the angle of refraction gives us the angle of incidence. At point B, the angle of incidence, angle of reflection, and the deviation add up to pi. At point C, the deviation plus the angle of incidence adds up to the angle of refraction. So, noting these three observations and the results of part A, we reach the total angular deviation from the original trajectory. And if I write Snell's law at point A, 1 times sine of the angle of incidence is n times sine of the angle of refraction. This tells me that the angle of refraction at point A can be written in terms of the angle of incidence at point A and the index of refraction. And if I substitute that for 4 times the angle of refraction at point A, you can see that all of the deviation can be written in terms of the angle of incidence and the index of refraction of the medium.